Hello and welcome to our virtual Lunch and Learn. Today we're talking about drives installation best practices. This is part one of a two-part series we're doing this week and next week, so be sure to tune in next week for part two. My name is Rachel Green. I'm the Digital Communications Specialist here at McNaughton-McKay Electric Company. And presenting for us today is Les Smith, Systems Consultant out of our Toledo, Ohio branch. Out in the comments section, ready to answer your questions, is Lee Smith, Drives Product Manager out of our Charlotte, North Carolina location. We'll also have a Q&A portion at the end for Les to answer your questions in more depth. We'll be getting started shortly, but we'd like to allow a few minutes for attendees to join us. As you come in, let us know where you're tuning in from in the comments. We've shared a link to a short quiz in the comments section that Les will be referring to later in his presentation. Feel free to download, print, or have the quiz on your device for easy reference. Hi, Jody. Thanks for joining us. For anyone just coming in, welcome to our virtual Lunch and Learn Drives Installation Best Practices Part 1. Let us know where you're joining us from in the comments section. We'll be looking for your questions as you have them, while our comments are covered by Lee Smith, who is our Drives Product Manager out of Charlotte, North Carolina. And Les Smith will be covering important developments in drive installation practices and what you need to know as an installer. If you'd like to reach out afterwards or if you have further questions for Les, you can always send us an email at macandmaclive@macandmac.com. Be sure to let us know what session you attended and we'll get your questions to Les. Looks like we have quite a few attendees joining us now, so let's get started. Les, I will pass it over to you now.
Thank you, Rachel, and also thank you, Leanne, for helping put this together. We'll just get going here on the presentation and we'll comment during that. Send your questions in as needed to Lee, and he'll take care of it for you. And also, I want to thank Randy and Gerald out there, my other associates. They handle industrial control and safety, and they may make comment as needed too. Okay, here we have my index that I put on the front of all my slide presentations. We have 62 slides, and we'll do half of them today, around half, about a half hour or so. And on the right, you see a line to load description. And this presentation started about 5 years ago or so. And I noticed that there was trouble out in the industrial scene where I was getting called on drives that were not starting up smoothly because of application or installation problems. So I started looking around and trying to find a way to help our customers understand better drive installation. And getting over to the right, line to load didn't exist at that time. And what I found was I found a vendor presentation that was very close to that, and I added to it. And shortly after that, Alan Bradley put the line to load description back in there to give us a pictorial on a drive installation. Oh, and don't forget the quiz. As Rachel said, you can download that. The reason is, if you want, I can give you a certificate. The certificate and $1 at McDonald's gets you a cup of coffee. But we do that in town for the people that have PE and got to show continuing interest in the technology, and that's available to you also. On installations, does this look a lot like your plant? And you can tell here, and over here, looks like an explosion in a spaghetti factory where you got wires running everywhere. And this may not happen initially, but troubleshooting, you pull the duct covers off and the wires start to go all over. And this gets sensitive wires too close to power wires. You can see the black and the blue, which would be 480 volt and 24 volt. They get close together, and they can, in fact, transfer a noise from power to control and cause headaches. In the middle here, now that we have our cards are all coded, we can withstand the environments that we have out there that are somewhat harsher. However, I'll make a statement, they're coded right up to the screw connection on terminal boards. So if they have an example where they installed a circuit board out next to the ocean, the salt water actually came up the wire and hit the screw and then started to corrode the terminals on there. So it's very important that you watch your environment out here. Also over here, magnetic dust, dust in the air. I once had an occasion where a drive blew up 300 horsepower, and we actually took a cup of metal shavings out of that drive because they left the door open. And here's an old familiar one over here. These drives are mounted too close here. We need 2 inches plus in here. Just follow the installation guidelines on your user's manual. But another important thing is to elevate these so that the fans are actually pushing over the top of the duct, because what happens is it causes the components to dry out. And you go to power up a drive one day, once you shut it down, it will not power up because the components won't come alive again because they're dried out. And we're talking about a little upfront saves a lot of work. We have guidelines and rules and recommendations out there, and it's documented throughout the industry. This is not unique to any particular vendor. If you take a look out there, a lot of vendors will be pushing documentation of very similar nature on installing of their drives. And take a look at compliance of RoHS. We're taking the heavy metal out of the circuit boards. That makes them more susceptible to the environment, and also the components are getting closer together, so they're even more susceptible. So as we go on in time, our components need to be protected more. So, and the bottom line there is proper installation and drive in the drive environment will help extend drive life and performance. I see drives going 15 and 20 years out as a normal life if they're protected and they're in a pump or fan application. You change the environment, you change some jumpers, and that shortens the life. The problems are obvious. Unintentional machine stopping. We have errors or accuracy that can be in registrations and dimensioning, feeders, etc. Batches aren't correct, and the control process is not running smoothly. Network communications can appear, and you're unable to listen to the telephone. If I have a drive down in a manhole next to a stoplight, we should put a filter on it so when you're sitting there, you don't hear the drive ramping up, pumping the sludge water out of the town. Damage to electric equipment. We'll touch on this many times more down the road here. Overall impacts: loss of production, loss of revenue, increased cost, time delays in commissioning, increased cost, and that hurts everybody. Now, when I started this, I started to look through the information that was allowed me by my vendor. And you take a look here, the top two, drives-IN001 and drives-AT, etc. These are guidelines. They're not specific to any series of drives, but they're general for all sorts of drives, not just one vendor, all sorts. I saw the wiring and grounding guidelines. I saw online where the ham wave operators were using this on installation of their ham transmitters. Now the AB series specific or brand specific there, 1321, 750, 520, these relate directly to that product. So there's different manuals out there. As you see down in the bottom there, across the bottom, you see some symbols. And I'm going to try to put those symbols at the top of each page, and that's where the reference is. You got your drive installation manual, IN001. That's about a 300-page document on the drive installation. And then the drives AT industry, they use 20 checkpoints consistently for the different industries out there: petroleum, logging, automotive. But then they have a reference to manuals of that industry that pertain to the installations in the different industries. The 1321, I got that in there specifically for common mode chokes. That one actually tells you how to wrap or wire your own. And then the 11E, that's the power jumpers. Everybody's got jumpers for grounded and ungrounded systems. And if you went back up to the to 750 right above it, IN01, or right below it, on about page 250, you'll find reference to the jumpers. But if you take a look at the power jumper one, that's a 12-page document that covers something very similarly. So as you take a look across the bottom, those symbols will occur clear at the top, and that'll tell you where I got my information. I try to get most of my information from documentation. Other than that, I'll have opinion. And as you see here, I started to look at how to put in a drive, and the quadruple diamond up there in the upper left says that this is the quick start, 750 QS. It's a very good book for putting in 750 drives. It has programming examples, it has wiring examples on a much shorter string of information, easier to read and specific to startups. But what I looked at here was gather required information, being aware of what you have in front of you. And we take a look, the nameplate on a drive will tell you the frame size. The frame size will relate to options available relative to that frame size. Firmware level will tell us when that drive was commissioned, and if we want to accept that firmware level or flash it back in case of replacement. Normal duty, heavy duty, this is the rating and derating of the drive needed per application. Minimum dynamic braking ohms, that will be on the nameplate, and associated hardware. Manufacturing date and serial number would be dealt with directly on warranty basis. On the right-hand side, I encourage using software. You can use Connected Components Workbench, which is free software downloadable from the website, or Drive Executive, which is an aging software, works very nice with the older drives and PowerFlex, but will be going away in the future. Drive Observer is a trending software. I like to run trends so that I can come back and look at what the amperage was, what the voltage was, what the speed was relative to the process, and have a picture of it so that I can better understand it and or pass it along to the customer so they can understand. And then you got down at the bottom, you got your Logix or Studio software, which will also be able to troubleshoot the drive for you. Note here, review the installation manuals for ambient temperatures and altitudes for derating. That's very important. And here they call on output contactors next one down. That's not as popular today as it was in the older drives, but they make note of it a lot. So I kept it in there. And we'll say in the same manual here, and this is, I'm asking where you get the information off the nameplate, be aware. And I realize you may have dozens or hundreds of motors out there, but understand when I come out, I usually have just one motor to look at. So I hone in on that so I can get a better understanding of that particular application. In each drive, you're going to have motor nameplate data. And as you see, you got the volts, the amps, the hertz, the RPM, the power units, be it watts or horsepower, and then the power level that you're going to put in there. The number of poles, please don't put down 3 poles. I see that so many times. And motor overload factor. Take a look at motor overload factor on the 753. That's on parameter 413. That's 400 parameters away. You may miss that sometimes. Motor speed range, you look at the motor for that. It's 10 to 1 speed range, 2 to 1 if there's no derating, 10 to 1 20 to 1, 1,000 to 1, 2,000 to 1, depending upon the quality of the motor. But be aware of that so you can watch the process, see how it runs. If you don't stay within those parameters, you're going to get motor overheating and damage. Mechanical brake coil, see what's tied onto that motor. That's important to know for startup, especially to do tuning. You unlock the brake, but then to know where the wiring is for that coil. That's an inductor out there, and it could be close to some sensitive wires. Drive wire length. How far is the drive from the motor? Very important. One of the first questions, is it 5 feet or is it 300 feet? That determines a different strategy in troubleshooting. Encoder present or not, and the brake contactor wire. And as you see over here to the right, the brake contactor here, the wire, there's the contactor, and here's the brake itself. You treat this different than you do these over here. This is the drive wire. There's the encoder. Again, just using that diagram to help get a picture in your mind. Look at your motor nameplate. It's going to say if it's inverter duty, high efficient. That's important on tuning. Shaft ground rings. Certain horsepowers, you're going to get some ground rings by default in there for common mode noise, which is nice to know. And then the motor data itself. I'll go back to high efficient. Some of these motors are getting very efficient. And for instance, you can get a motor out there that has 1790 RPM. The drive may have trouble with that because the slip is so tight that you may have to go into a different mode than you're used to on that. I found that I go into the more complex modes, the vector mode, it handles those motors better. But again, just understanding what you have a hold of when you get out there to do startup. Oh, here's the note. This is your volts per hertz. On a 460 volt motor, 60 hertz, your volts per hertz rating is 7.67. That is where your performance is based on. You got to get the motor nameplate data in there in order to get maximum performance. If you're 230, it's half that. That's very important to understand and to know. Motor overload fault, we talked about that. This parameter is directly related to that fault. In other words, if you get a motor overload fault, it's relative to what you put in there. It could be a factory default at 1.0. It's not a service factor, but you may need to bump it up to keep it running. I had a fan in a hospital, in an x-ray room, where it pulled a tenth to an amp higher than what the motor nameplate was. But it didn't trip out until 12 to 20 hours later on the emergency room. So we bumped up the motor overload. That's what keeps it running, as the motor overload setting. Whereas if we take a look here, the 3 asterisks up there, motor nameplate, that's just used for tuning. So if you put the motor nameplate in there, if you do a static tune, the drive will actually throw out that much current DC wise, because it's rotational, and we'll do an Ohm's law calibrate out there. That's all that's used for. So understand these different parameters mean different things to getting your production drive up and running and keeping it running. Grounding and power connections. That's one of the first things I go to. Now you notice here, okay, our reference here is still the quick start at the top for that question, but you see the solid triangle, that's in the AT003. On the quiz, a lot of those questions are related to that, but they phrased them so they were easy to use here. Verify that an isolation transformer is installed or not, but be aware of it. Is it grounded or not? Verify that XO on the secondary of the isolation transformer is solidly grounded. Less than 1 ohm is the definition of solid ground. Verify the isolation transformer is good quality. Sometimes transformers of lesser quality can give you more problems down the road, even on installation. I've had contractors that liked the beefier transformers for lifting, etc., because it was quicker to install as far as rigging. Verify the isolation transformer KVA does not exceed 10 times the KVA of the drive. This has to do with the amount of energy that that drive will accept on power up. 10 times rule is for your component drives, or drives that don't have an inductor between the converter and the inverter. Now, the automotive or architectural drives will have a inductor between the converter and inverter, and it can take 20 times the size of the transformer. We'll talk about this a little bit later. Line reactors are highly recommended if transformers are not used, and they add the impedance up front on the drive. No device shall be wired between the reactor and the drive. This note was pulled through in that other document. You'll see a lot of these comments duplicated. Verify power wiring connections, just even checking L1, 2, and 3, making sure that they are wired directly from the power source. And then the T1, 2, and 3 are going to the motor. Yes, I have seen drives get wired backwards. Proper ground wire terminations go to the PE ground studs. Each drive will have one ground stud each, incoming power and outgoing power. They happen to be connected to the same bar, but symbolically it's nice to wire left on the in, right on the out wire. Drive jumpers should be all in or all out. I got a quote from President Ronald Reagan, and this is a Russian proverb: trust but verify. If I'm out on the site and I'm talking with customers, you're going to hear me ask the same question 3 times. Is the transformer grounded? Have you seen that ground wire? And take a look here. This transformer, the XO is there, and on this transformer, the XO is here. I really need to know if that actually happened, and we'll talk about this a little bit later. Speaking of those ground jumpers, all in or all out? What does it just read it here? Properly configured drive has all jumpers connected or disconnected. Solid ground, all in. Non-solid ground, greater than 1 ohm, all disconnected, or high resistance, all disconnected. And you see various wiring diagrams. PEA and PEB are what we're going to see in our drives up to about 400 horsepower. PEB here, you see this jumper. These capacitors are actually the same capacitors for the bus charging. We just happen to have a jumper in the middle, and we take the ground and we use these to filter the noise that may be out there to ground. PEA, right here, these are the metal oxide varistors, MOV, and the capacitor filters out there. And in the old days when we had the older drives, this MOV would be bigger than the others. And if we did have an ungrounded system and we sensed problems, we would take some side cutters in there and clip that wire. That would be a bigger MOV than the other ones. But anyway, that's your wiring. So these are both in or both out. On the bigger drives, frame 8 through 10, they have a little different jumper wiring here. They have PEA1 and PEA2. Now, I've thrown the 520 in here. It has a separate jumper here, placed thusly. You put the screwdriver behind the plastic, go down, loosen up the drive, pull out this little horseshoe-like jumper, and then tighten the screw back up. Unbalanced, ungrounded, resisted, grounded systems, remove the MOV jumper and remove the common mode jumper there. Now, we'll talk just a little bit about frames. The drives come in various physical sizes, so they move the jumpers around on us sometimes. Here's the frame 1. We won't be talking about that today. That's just a smaller drive for compact applications. This is a frame 2, and so right here, the 2 jumpers. It's a screw head that goes on top of a U-shaped jumper, and and it shorts the 2 U's together, or 2 Y's together. And same thing on frame 3 and frame 4. Now on frame 5, we separate them a little bit. Now we go up to frame 6 and 7, and look, we move this one down here and this one up here. very similar on the frame 7. That goes up to 400 horsepower. Now, when it's ungrounded, all you're going to find is a plastic hole that you screw the screw into and tighten the pigtail down, and that is the ungrounded. Over here, frame 8, 9, and 10, you're going to see that when you see an 8 is nothing put together. You double it and you get a frame 9, you triple it and you get a frame 10. This one, you actually, the jumpers are actually plug and unpluggable. So you see here that we disconnect it, we move it up to here and put it in that socket. And when we connect it, we put it down to here. And that's PEA2. And PEA1, very similar here. We attach it to a metal stud here, and we connect it to a plastic stud here for ungrounded. On that, we actually have to take the drive apart to get in and move some jumpers around on that one. Enough on jumpers. The next subject I had, and that came out of the quick start, as you see by the symbol up here, was 3 places where signal sources are connected to the drive. I wanted the startup people to know where to look for what type of wires. And over here, the drive's main control board, since this is a slot drive, it's called DPI 0 on either the 753 and 755 is clear to the right over here. 753 has some I/O on it, and here the 755, it has an Ethernet port on it, and it's got one input on the 755, and that's separate from the motherboard in the location. It's down here. You have to have a dental mirror to find it. But again, just knowing where to look for this. Then we have I/O cards that we can add. We have 3 to 5 slots that can have different I/Os in encoders, digital I/O, COM cards in them. And here's the COM card that can be added to either one if you wanted to have dual COM cards on the 755. But being aware of where that's at, the drive can always be run from the HIM without having any wires run to it, just for testing purposes. And here's indications on where things are at. This is the motherboard, DPI 0. Same thing over here. You can see on the 755, here's your last octet adjustment for the Ethernet. And over here, since the 753 doesn't have that, we add that over to slot 5. You can see the slot numbers here. As you can in the picture of my demo here, there's slot 5. Digital I/O card is in slot 4. COM card is in slot 6. Just be aware of that. Another thing that I brought out here, analog signals. And this happens to deal with an encoder. If we take a look over here, the important thing to see here is that a 24 gauge wire can run 300 to 400 feet off an encoder and be accurate. However, the power cable, the power to that encoder may have to go up to an 18 gauge, but this shows you the various cables that should be there. One thing about encoder cables, look at the vendor spec. We need low capacitance cables. I've had where we've had 300-foot runs and we could run up to 40 hertz, 45 hertz, and then we get errors if we tried to go faster, and the capacitance in the wire would draw the power away from the encoder pulses. It would pull it, capacitively couple it. So you had to have the right cable there. Even if you had the right cable, be aware down here that there are different drivers. Typically, you get a 72 driver on encoders that you buy, any brand on that. But if you was going farther, 100 feet to 300 feet, you may want to opt for a 4469 driver, which gives you 300 foot. And here's the driving. This has 4 to 50 milliamp capability from the encoder back to the card, where we have 100 milliamp here. The other thing is keep that wire, the encoder cable, away from power, about 12 inches. Something like that might appear on the quiz. Verify the encoder cable outside of the enclosure is run in raceways using dividers and or separate conduit runs on that. I put this up over here. The encoder feedback, if it's a quadrature, you're going to get 4096 pulses for a 1024 encoder. Sometimes I've come across encoders that were existing. All the literature was gone off the output. I couldn't read it, so I just did an output, one rotation, and I can see 4096 show up here. Encoder status, which is here. It's hard to troubleshoot an encoder because the screws are so small that you can just look here, and that brings your points up here for B or B not. And if you have a check mark on every other one, it's healthy. But when you get check marks close to each other, then you may have a potential problem. Pull that connector off and you'll see those check marks come together, and you'll see a fault show up on that. We're under associated equipment here. And again, off of the AT003, verify the dynamic brake is installed to BR1 and BR2. It may not always be BR1, BR2, might be BR plus, BR minus, but there will be two connections on a drive if it has a chopper to attach that resistor to it. I check that to make sure that it is. Verify the dynamic brake cable is twisted pair. If you have dynamic brake cables, they should be twisted. And if you have a shield, don't attach it to the drive, attach it to the ground bus of the panel. And there's the knowledge base note for the dynamic brake cable, 722667. Just put a twist every foot to cancel out the noise that can come from that. And then do a resistance check. And that's my initials, and I was born in 1950. You can just easily, the drive's powered down, put that ohm meter across there and get a reading out there. Here's that temperature snap switch that comes inside of the dynamic braking resistor that nobody uses. And this is how it's supposed to be used. It's supposed to go to a starter contactor, and that is supposed to power the drive up. If the snap switch gets too hot, it opens up, takes power away from the drive. This happened, let's just say 15 years ago. We had a power surge through mid-Ohio, and I lost 9 drives out at a customer's place because the chopper is still working even if the drive's not turned on. And we had power surges that went up above the threshold and turned on the dynamic braking resistors. It didn't happen to drives that had isolation transformers on them. But my customer lost a lot of drives and resistors. They burn them up. And here on the drives, if we're doing dynamic braking resistors, there's going to be parameters relative to the drive dynamic brake setting. Here, first of all, we're going to turn the bus regulator off, and we're going to turn on dynamic brake. It says only because there's some other settings on the architectural drive, which means dynamic brake first, and then frequency adjust, or frequency adjust and then dynamic brake. And what that means is there's another manual out there called a 750-RM reference manual. And it'll tell you that that chopper will turn on 8 volts before the normal threshold if it's just a dynamic brake only. So you have 2 levels that the dynamic brake will come on. It'll let the drive try to correct things. And if it doesn't, it'll throw the chopper on to do some braking out there. We're going to tell it that it's an external resistor. There are internal braking resistors on the smaller drives. If these are used, they're low power, they should be noted, but pick external. The ohms of the resistor, this one happens to be 45, and the wattage, 3600. The DBR watts, same as joules. You can call me and I'll give that to you. I have the tool to do that, or you can do research on the web and find it, or you can call the dynamic braking resistor vendor. And this one, it happened to be 188,000. Drive comes with 2,000. This parameter tells you how much energy we're going to put into this resistor. If we have more energy than what this resistor can handle, go to a status word, specifically 945, and there'll be a bit in there that says we've exerted the energy of that resistor. Now we're going to give you a little bit of French here, okay? Débarras, okay? Remember that. What that stands for in French is dynamic braking resistor rule of thumb. And if you take an 8 ohm resistor, it has 100 horsepower worth of braking torque if it's put across the bus of the drive, which is what the chopper does. If you have an 80 ohm resistor, that's 10 horsepower worth of braking. From that, you can tell what ohmage you may want or should be close out there on that resistor. For instance, let's take a look at ours. We have 45 ohms. This is a 15 horsepower drive. And if you look at the nameplate or look it up, the minimum resistor on this is 22.6. If a motor can brake 150% up to 200%, you're going to see that reflected in this resistor. This resistor is roughly half of what the 10 ohm is. So we got about a 20 horsepower braking torque on this resistor. So you can see resistors out there and you can just estimate. And this is just a rule of thumb that you can be quicker on your feet out in the field. Okay, associated equipment, mechanical brake. Here we go. We're going to look at the brake out here. This is actually the coil, the mechanism that moves the brake plates together. Mechanical motor brake coils must be suppressed. And I found that in this article right here. And it says must be suppressed, refer to wiring guidelines. And that one is this guy down here. So it evidently appeared in both. You can use RC networks or diode or solid state on them, however you find the sources. Mechanical brake control cable right here. Again, they're going to talk about the shield and it not go to the drive, go to the backplate ground. Drive wire, that's this wire right here. This is the first time we've mentioned this. The cable, shield, and ground must be connected to both the drive end and the motor end. And daily, I find that you're not connecting the shield at both ends, along with the PE wire. And this is a different philosophy than when you're putting in instrumentation wire, etc. You only connect the shield at one end, source end of power, in that industry. We connect it on both ends. We want a path for noise to go through. And show you a field disconnect out here, and I've plagiarized it here. I put isolated terminal blocks here. Normally you would find a terminal block in there that would be yellow and green, and then it would clamp right onto the ground. And you notice this particular disconnect here has a metal backplate here that goes to the conduit here and up to here, and probably is connected to these terminal blocks here. I don't want that shield to get grounded anyplace else besides at the drive and at the motor. We will create ground loops. So just move the ground wire out around or change the terminal block to a non-grounded one and use it. I've noticed some other field disconnects don't have this metal in, and I've actually ohmed out that ground connector and it was insulated. That's up to your integrity to check that out. But this is the general consensus here. Oh, this one here, we're talking about surge suppressors. And what's the surge suppressor to use? Well, I happen to find a page that would tell me what surge suppressor to use on what coil. And I used it religiously, so I didn't have to look any farther. And I would ask that you find your own source out there for whatever components you have to use surge suppressors on all inductive coils that you have in the panel, whether they be a diode or an RC circuit. Okay, this is the beginning of the vendor's PowerPoints, and this is where their attempt to enlighten people on drive installation. So we might find some redundancy here, but this is a vendor originated here. We're going to have a drive input and the drive panel and the drive output relative to this circuit over here. And a source, we're going to talk about source impedance. We're going to hit grounding again. And then environment, clearance, and environment is the specifications, and the atmosphere. And then the power jumper configurations and the ground practices. Drive output, cable length, properties, and routing. Okay, we're using the right here, grounding and bonding drive installation book here. It will have tables in it for you. And the tables will relate to the drive, specific vendor drive that you're using, and give you guidelines for when to use, for instance, reactors, filters, etc. And that is right here after the reactor and before going into the drive. More specifically, right here, we're going to look at the PowerFlex 525 drives and the PowerFlex 753, 755 drives. Just FYI, the 753 and 755 are identical in power structure. The only difference is the motherboard and a backplane board. You can convert one to the other either way. Now let's get back to here. And I found it most useful to look at the 5 horsepower drive. We look at the 5 horsepower drive here on a 525, and it says the transformer, the maximum kVA would be 50 kVA for it without using anything in front of it. Anything bigger than that, you would use a line reactor, and there's the part number, which would mean it'd be an 18 amp reactor. Over here, let's take a look at a 5 horsepower and see if we can find it here. Okay, 5 horsepower on a 753. Now, it is the maximum supply you can put on that, so 500 kVA. Now, I believe the other one was 100 kVA. There's 5 times the size there, and that has to do with the inductor that's between the converter and inverter. That is in the 755. On all of these, see where this is grayed out? This guy doesn't have an inductor into it. And I think there may be an inductor on the very largest size, but you can see how it affects how big the transformer can be without the influence of damage. So that table will be for all the drives specifically, and you should check on installation what your power distribution is. That would aid you in a decision to put reactors in or not. Speaking of reactors, when do we add a reactor? I've handed this out to many people. Low impedance, less than 1%, highly recommended to put in a line reactor. Supply, the kVA is over 10 or 20, depending on what we just spoke about. Put a line reactor in. Power factor capacitors it depends if they're switched or floating. Line has frequent power interruptions. It's at the far point of the plant, the last one of the road, where you have a lot of interruptions. Or we have intermittent noise spikes. Say you got the 100, 200, 300 horsepower motor on a starter that is picked up and dropped out. You may have an inductive spike coming back. We put the reactor in there. Incoming voltage imbalance greater than 2%. The reactor fights the urge of change. If the voltage goes up or the voltage goes down for milliseconds, that reactor will hold that energy. Again, here we go, grounding as stated, as solid ground less than 1, high resistance ground greater than 1, or ungrounded. And the drives can go with either grounded or ungrounded. You just have to arrange the jumpers per the literature. Here we're just going to look quickly at the types. Here we have a grounded Y, and the statement here is only system allowed for CE compliance. You're not CE compliant or you're not UL compliant unless you have a grounded. We're running out of time. We're going to speed up a little bit here. Here we go. Delta Y. Take a look. This is the transformer we had back in the beginning. Take a look at this guy here. Here's where the customer actually ran the ground. He brought all the grounds back, butt spliced them together right here, and then 4 foot away from the XO, he tied that to ground. I blessed it and said, yes, it's grounded. I've actually had second thoughts since then. If we're balanced, we shouldn't have much current here. But if we're not, we may have a little bit more current here than what this joint can handle. I might change my mind today and say ungrounded, and I would pull out the resistor or the jumpers on that. So that's the first example. Here's the second example. Remember this transformer here? Here's the XO, nothing attached to it. That's right here. However, you got your ground wire coming in from the power attached to here. This is what the nameplate on the transformer said. Neutral is bonded right there. It wasn't. It's open like this. And again, I asked, and we finally took the cover off of this big bad boy. This was 300 horsepower. So it's probably 250 kVA. And we saw this. And this one, we had all the jumpers come out. We deemed it ungrounded. And this is a high resistance ground. We put a resistor in the ground here. Either leg, any leg can go to ground and will continue to run. And at a later point, we'll come out and find the ground because we'll have indicators out here that says we're grounded, but we continue to run. I find that still applied today right next to transformers that are grounded. I have single plants that have both systems in them. And here's a Y delta or delta delta, totally ungrounded on this. And the dangers are your ground can rise up and cause damage to your components. And again, here's the statement off of this document here. Makes the statement, UL compliance, reduced electrical noise, most stable operation, EMC compliance, reduced voltage stress on components and motor bearings. And we'll talk about that next week. Oh, here you go. Here is the nameplate, or this sticker comes on every 750 drive. Do you see that out there? That should be stuck somewhere around the drive, but this asks you to go read about the grounding system. That's on every architectural drive that's shipped. Here's the reason for that ground jumper. This is the PEB jumper. If I put the ground jumper in here, look at this. The noise is between 500 and 250. We have 250 volt of noise that will be riding on this bus. Pull this jumper out. Now look, we have the noise going up to over 1,000 volts, and that's on the bus because we're not filtering it out. The ratings on the capacitors, overvolt rating on a drive is 810 volts. Those capacitors have a rating of 800 volts. So what we have is we have this agitation of the components in that drive all the time, which will cause a shorter life. That's why we like to have a grounded system. Okay, this is our last slide, I think. Right here's our grounding, PE ground here and here. More important to me is these notes here. Verify the paint is scraped away down to the bare metal when you put the ground bar in. Better yet, put a galvanized backplate in. Verify ground wire is run from the power transformer XO directly to the drive PE. And then verify the ground wire is run from the motor directly to the drive PE. Verify sub-panels are bonded together using braided metal straps. The noise we're talking about prefers fine wire as opposed to solid wire. So we're half done. That's what we have for right now. I'm going to hand this back to Rachel. Again, there's a quiz up there that you can download. We'll offer a certificate. You get that quiz back to us. It's all filled out, and we'll send that to you. And Rachel, you can have it back now.
Great, thank you, Les. We do not have any questions in the comment section at this time, but I'd like to allow a few moments in case anyone has follow-up questions for you. And while we wait, I'd like to remind you that you can always reach out to us at the email address there on the screen, macandmaclive@macandmac.com. As Les said, feel free to reach out if you are interested in receiving a certification of completion at the end of this series. We're happy to provide that for you, but please note that it does not fulfill CEU or PDH requirements. You can also send us your questions even after this live stream has ended, and we'll pass them along to Les, who can reach out to you directly with an answer. Just be sure to let us know the title of the session that you attended so we can get it to him. Wonderful. Thank you, Les. Thank you, Lee, for being our resource out in the comments section and adding some comments there for our viewers. I want to thank you all, our live viewers today, for joining us, and we hope this session was informative and engaging for you. Remember to subscribe to the McNaughton-McKay YouTube channel for more industry content, and join us again next Wednesday at noon Eastern for part 2 of Les's Drives Installation Best Practices series. Thank you all, and have a great day. All right, Les, you there?